Does everyone see the presentation? Or does someone see it?
Yes.
Okay,
Yeah.
so it's correct. Good. All right. Okay, so I'm Christopher Swank. I'll be talking about the sort of work that I've done for the SNS EDM experiment. Let's so I, yeah, so go over a little bit about the SNS experiment and EDMs in general, a little bit for the neutron electric dipole moment. And so I'll go over the signal generation for
Chris, your voice is breaking up.
maybe I can. Okay,
That's
so okay, good. Spin dressing technique for perturbation theory that was developed a couple of years ago. From these sort of theories, I talk about how we can optimize our fields. Experiments. Design that I used after I've developed sort of these optimization techniques.
Chris, your voice is still not clear. Can you dial in instead of using the internet link?
Okay, it's breaking up. Is that what it's?
Yeah.
Internet issue? Okay. Yeah, I can dial in. You'll have to give me a couple minutes. Maybe I can dial in. I can't seem to find. Does anyone have a phone number that they can post on it on the chat, perhaps? Because I can't find it in the email. All I see is a Zoom link.
Oh,
if you go to your mute option, so the little caret next to the mute microphone, you can do switch to phone audio.
Okay.
Your phone's good now.
But the voice is also working well now. So if you want to roll the dice.
I don't even know which one it's coming from now. Is it this one? Can you hear me still? Hello?
Yes, we can hear you still.
Okay. All right. Well, all right. Okay, so I'll just continue then.
The other mic was better.
The other mic.
Or we can't hear you now very strongly.
You're very quiet.
It was good in the beginning in terms of
Hello?
volume, and then it went very
Working.
faint, as if you like walked away a meter or two or something.
How does this work every other time in the universe except for now? I guess I'll just dial in. Hello? Hello? Now I
Hi,
can't
Chris.
hear anyone.
That's
Okay.
that's good
Is this
voice.
better?
Do you mind backing up one slide? That's great.
Okay. Yeah, so this is the, oh, whatever. Right. I don't know where I was breaking up. So I'll be talking about sort of the EDM, giving a brief overview of how that experiment works. Then I'll go over some tech and some relaxation techniques. And then I go over spin dressing and sort of continue with these with spin relaxation frequency shifts. And then I optimize the coil based on that work. Or I, propose an optimization method based on that work, and then I proceed to show how that works with the SNS and these pulse star design, coil designs. Okay. So this is a schematic of the or a visual of the EDM apparatus with the shielding. So this is a neutron cryogenic experiment. The neutrons get beamed into the cells where they downscatter and turn into ultra cold neutrons from the helium superfluid helium phonon process. And you'll notice that the cells are rectangular, and that's sort of an important component of this field design. It sort of allows us to take some simplifications. Anyway, I should get going. So this is the neutron SNS EDM. The signal comes from scintillation light from this neutron capture on helium-3, which produces a triton and a proton and 764 keV. And so our signal is proportional to this sort of theta here, or this cosine theta, or this sigma n dot sigma 3, where our signal, if you reverse the field, is due to this phase difference between the up and the down field orientations. And so this is a spin precession measurement. And so we have to worry about all the things that spin precession measurements do. And that is mostly, we have to worry about coherence time. So we want to increase our coherence time. The neutron, decays at some, I really wish this bar would be smaller. The neutron decays with some, at 880 seconds. And the coherence, should be much longer than this. So we want to design our field so that this is the main decay process of the experiment. So we're in the red field regime, and what I mean by that is that the relaxation is much longer than the time it takes to diffuse around the cell. To so the correlation time goes to 0 much sooner than the much quicker than the spins relax. And so we're in the red field regime, so we can use these sort of correlation functions to predict our relaxation. And where the largest contribution is generally the 0 frequency term here. And so if you're in a linear gradient, this is just the autocorrelation function and the spectrum of that. And you can write this as a conditional probability. And so the idea be to minimize this. There's also a troubling systematic effect for EDM, and this is this geometric phase. So there's also a frequency shift that comes from the interaction of the E field and the B field. And here's sort of an example of this. This was one of the experiment. This sort of in 2006, this sort of forced them to stop taking data because this was the large effect that they weren't going to end up beating. So this is sort of the reason why we want to keep these fields. Another reason we keep these fields. So a little visualization. So if you're in an E field and a B field, and you're sort of in this rectangular cell here, what you'll do is you'll rotate, the V cross E rotates along this x-axis, and this gradient, it doesn't contribute any rotation at first because it's at 0 if you start on this wall. But as you progress through the trap, you end up creating a rotation due to this gradient in the Y field. And so if you start here and you come along, you first start to rotate up due to the V cross E, or down, I guess, in this picture. And then you start curling around due to the B field. And then on the way back, you experience it in sort of the reverse order, and rotations don't commute. And so you end up with a phase accumulated and a relaxation. So that's generally how it works. The theoretical model, you can produce it from a field position correlation function, and then a field position volume average. So you can get at this field position correlation function at other ways. You can do it experimentally. You don't need an E field. You can do it with a gradient relaxation and solve it that way, or you can do actually frequency shifts, B field shifts, and get similar correlation functions to predict these things. Okay, so now I'm going to go into a little bit of spin dressing. This is the intro. So this is what our signal would look like in a typical FID if you ignore the relaxation. You get a beat frequency at the neutron and helium-3 difference of their frequencies. And so the signal we get is sort of the integration of this. And so you can see we would sort of get this as our signal, and where the number is you know, these integrals here. So if we can somehow take away the Siemens splitting, we can maximize our sensitivity. And this is where the spin dressing comes in. And so if we look at spin dressing, what we do is we apply an oscillating field represented by this A dagger A, and it interacts with the B field, the spin with the sigma X, A dagger A operator, and then we have this omega 0 as a perturbation. This is the Cohen-Tanucci's work. Where if we write this a wave function that solves this, and you take the expectation value, you end up with a cosine theta of this omega prime, where the omega prime is now shifted to the more precession by this Bessel's function. So critical dressing, so we can get rid of the critical dressing if we solve for this function here. If we just solve for this parameter alpha, where this alpha right around n is about 1.11 for neutrons and helium-3. And so you can see here that if we dress at this parameter, which turns out to be around 1.2 or 1.3, then you can match the Lamarck precessions. And so this gives us roughly a factor of 2 improvement, maybe a little more in sensitivity for this nEDM experiment. Here is a movie, hopefully. Okay. So this is what it looks like when you're dressing spins. These are at 2 different dressing frequencies. And you can see they mostly stay locked to each other, the angle. So that's, that creates a nice signal for us. We can modulate to get rid of sort of linear drifts by sort of changing the frequency at which we're dressing. And so we can basically flip this optimum theta for measurements back and forth, and this allows us to get rid of sort of linear drifts in the experiment. Okay, so we can apply a perturbation theory to this to figure out how spins will relax in this. We just add perturbation terms that we assume are small operators, and then we can, if we calculate sigma plus, which is Sx plus Isy, then we can figure out sort of how our spins behave, where our sort of our sigma plus dd, this is the 1 over the T2, and the frequency shift is the imaginary part. So the real part of this is the relaxation, and the imaginary part's the frequency shift. So when you do that, you get these terms that contribute. So this isn't too important to know, except for that we sort of pick up the original relaxation terms here, and if we're trying to evaluate sort of our geometric phases, then we want to evaluate at these omega primes, this omega prime value here. And so that basically is what we learned from that. There's no linear any frequency shift from dressing fields, so we don't have to worry about that part of the optimization. And there's also a weird effect where you get, if you can match the uniformity of the holding field with the dressing field, match their gradients, match their non-uniformities, then you get a vanishing relaxation. Whereas if the gradients are proportional to to this, if they match this ratio, then you get T2 is more or less approximately 0, where only these oscillating terms contribute, and they don't contribute as strongly. And this is nice because actually the gradient along the Z, you require around 15 times more amplitude because of this omega over omega 0, J1 and J0. So you're more sensitive, or you're less sensitive to this Z0. So you can get it sort of right and you will still have a big effect. This is shown sort of here, where if you only get it right to sort of 3%-ish level, you still end up with a huge gain in your T2. And so this is sort of what I take into account. So now we have sort of the idea of what we need to do. Now we need these conditional densities as well. This is where we take advantage of the SNS geometry. So this is a rectangle. And so if we're trying to get a conditional density of a rectangle, we can use the methods of images. And so any particle that sort of bounces off this wall and hits this observer, you can think of it as just propagating in free space and hitting this observer. And this, of course, only works with specular walls. So this is sort of what you end up with. Because these are repeating, you can write these as a Fourier series. And so you end up with a nice answer for this spectrum. You just have these field Fourier amplitudes. Another weird thing that sort of needs to be addressed is that if you do this in multiple dimensions, for a single velocity, you get sort of a different answer. And if you average these velocities, they don't, for each individual dimension, they don't actually correct themselves. So to fix this sort of problem with the random walk, what we had to do was we made a scattering site that was moving instead of stationary. And so what that does is as a walker comes in, it scatters with some V in, and the outgoing velocity is sampled from the distribution of the temperature of the gas. And so this can be written, the conditional density changes from just integrating sort of over a velocity distribution, but weighting it by the velocity distribution. So this sort of the propagator of just the unscattered propagation, the spectrum of that gets weighted in both the numerator and the denominator. So if you do that, what you end up with is something that agrees with diffusion theory. And so now we claim that, you know, we can more or less approximate to a high accuracy how these spins are behaving in our cell. And so from this, we can now start to look at how we should, you know, improve upon our coil design. And so the idea is that to first order, you can just minimize sort of this particle independent part, which is more or less just minimizing the RMS of the coil, of the field in the region of interest. And then there's this particle dependent part. What's sort of nice about this is that if you just pick the points, these Lx over x, you can just use the discrete Fourier transform to approximate this integral. And so it's sort of nice and easy, and you don't really have to simulate the spins. So if you do this, if you look at this coil, how these produces, so this is a 2D coil, and if you just do a regular cosine theta, you'll end up with sort of non-uniformities that look like this. And then if you optimize, use some like a def-min search in MATLAB or something, and you end up with this sort of field distribution on the right, which is obviously better. How does this look? If you're looking at the projected axis, so a cosine theta is just a uniform along the projected axis, whereas this, so you end up with a sort of a higher order change, and you see that it does sort of shift the ones close to the end of the coil the most, which is what Chris Crawford had mentioned in his talk, the dipole towards where your field is pointing has to be taken care of. So so if you include the conditional density, what you have is the neutrons are more or less ballistic, so they more or less go as 1 over q. The helium-3 has this nice error function here, which is sort of complicated, but if assume you're in the diffusion limit, which isn't completely true for the SNS nEDM, then you can use sort of this, and you see this q² behavior. So basically, we either want to minimize the square root of the Lx squared or just the Lx squared for helium-3. Typically, I minimize for neutrons. So this is again another toy model comparison of the two methods. So without the conditional density, you end up with, both of these fields are very good, but with the conditional density, you see you get some T2 that's 4 times longer. And, so none of these coils are actually, this is obviously 2D, and none of these are realizable. because the precision of the wire windings would have to be much greater than is currently technologically available to us. But it's sort of an interesting idea when you have to start adding defects and things. This does actually allow you to play around with coils and get stuff. It's still working. Hello?
Yeah, you're back.
We lost you.
Hello? People hear me again?
Yes.
Sorry, my headset turned itself off. Right. I had a timer, but now it's gone. Maybe I'm at 20 minutes. Okay. Okay. Where was I? All right. So I applied this to. This is a coil I applied it to for Pulsar. I'll be talking about that in a little bit. And so this is a coil that I applied it to that had PMT light guides here. You can see. And this is, so this is basically the minimization technique that I would claim, sort of that I used is basically take something that's from like a Chris Crawford method where you find a scalar potential that's perfect, and then you make these wires from these contours. Then you solve the model with these wires that, and I do all this in MATLAB pretty much. And then I optimize the contours via minimization of this relaxation based on the theory within MATLAB, and then I just optimize on that. So the optimizer controls the value of the scalar potential, or the difference between the wires, and then MATLAB's fmin search algorithm to achieve the minimization of this. And you get this nice coil. This coil turned out to actually not be good enough, and that's because the cell in this, okay, so the cell in this is along the direction. I don't know if you can see my mouse moving. It's along this direction. It's along the axis of these PMT, the PMT guides, the light guides. And it's 40 centimeters long in that direction. And this is only roughly 60 centimeters wide. So you only have 10 centimeters on either side to hit the coil. And it just, and sort of these currents here just didn't, so I was never able to get this model to work. Eventually they did away with PMTs and light guides and these wires, but also there was a better method that was proposed, and this was of course originally proposed by Chris Crawford, but using these superconducting end caps as a magnetic mirror. And so when you use these superconducting end caps, what it does is it more or less creates a situation where you're in 2D instead of 3D. At least that's what the models seem to suggest. And so here you can see, here's some current that's flowing around. And you see they become very flat when they finally get past this annulus here. So we demonstrated this in a small scale apparatus where here we tuned, so this is with, sort of minor shimming. We got a nice uniform field. Oh, sorry, I should probably say. So this is a probe on a track, and we oscillate it back and forth over 7 centimeters. In our region of interest, and so what we do is, as a function of time, we're getting a position of the field, and so we're oscillating it back and forth in the good field, and then as we run out of helium, and we did this for 6,000 seconds it looks like, so we ran out of helium, and then when we run out of helium you can see that the uniformity gets really bad, and the uniformity in this region is sort of hard to see, but it's sort of noisy, but if you just transform it, and you can see that there's a linear component that's very small, sort of on the order of 2 parts per V0 per centimeter, and then the quadratic component, which is larger at 6.3 10 to the minus 6, which is actually, these sort of fields are good enough for an EDM experiment. Okay, so I applied this to our V0 coil, where we use the Met glass flux return for our flux and superconducting end caps. And so this is sort of the design of this coil, an engineering goal. our engineering goal is 1 millimeter. We have sort of these things called story sticks and hoops and boss rings. These are what the engineers call it. And we have these tensioners, so we can do with any, cryogenic contractions. Okay, so this is another photo. This is the B0 and spin dressing. This is a little bit old, and so these are sort of what the models look like when you run them. And so this is a MATLAB output of the. Oh, here's my code. If anyone, I guess you can look at it later. So we made some of these rings. So you can't make rings big enough in G10. You have to buy them in parts, and so you have to glue them together yourself. And so we did this. We have a vacuum table, and we glue them together and pump them down. And so this is a view of that. So we did this for the ring that contained the wires, and then this grad student Swank, here's our group at Caltech, went around with this precise roamer arm measurement that we borrowed from LIGO, and he took measurements at each one of these points. So this is the deviation from the theta, and if I take the points that were given, which is sort of within our constraint, the constraints are there. If I take those points and put them back into the model, I get a really nice field. So it seems to be working. It seems like this method will work. So we've already produced 6 of these rings. Okay, so after you build the coil, I'd like to talk a little bit about how you would optimize it from if so you'll see a T2, and it probably won't be the greatest, but hopefully you'll be able to see it. How would you optimize this? And so this, I go over the ways you can do this with the relaxation of the helium-3. And so basically, you're going to be constrained to Maxwell's equations, and here are all these. Ooh, this isn't, the minus signs are wrong. All those minus signs are wrong. Anyway, so the green ones contribute to this T2. So if it's outlined in green, this will contribute to a T2. So you can use T2 to measure, how this varies. If you have shim coils that can excite these components, which are pretty easy to build for linear components, then how does this react? And so if you tune this knob, you're tuning this knob and this knob at the same time, and this one will sort of behave in a way that as you change the shim gradient, you'll get a maximum of T2, and as you change the shim gradient, you'll get a minimum on these frequency shifts. And then you can do this for all the different components. So for step 2, you want to do sort of the on-axis gradients, and you get frequency shifts and relaxations from these. And so you can just basically go through and at each step, just sort of tune based on your T2 and the frequency shifts, your fields in the end. For the shim coils, for the second order, it's a lot to worry about, and we don't really have too much space to build infinite shim coils in the SNS EDM. And so I did this to build the shim coil. I did it in a little bit of a different way. I just I scanned a wire as a function of theta and looked at the major components of T2 that it excited, so that this is basically the components of the T2 that will excite if we get a position that's wrong. And so what we can do is we can add some shim coils that sort of are on the minimum and maximum of sort of these curves. And so I was able to get reasonable results just placing wires there and then tuning. So you can tune the first 2 or 3 to be close to 0. So the optimization, so we start, so this is just the regular way I do it. So I jiggled the wires, and then I simulated what T2 we'd get from that, and then I approximated this as a 7 Hertz, and then I optimized the linear components by tuning shim coils and then seeing the effect of how it would work, and then I did the higher order ones after that, just based on T2. So this process, and I simulated all this. I've done this for real. But the whole process roughly takes, if you were to do this in a real apparatus, it would take roughly 18 hours for the SNS to go through one iteration of what I showed, and then 35 hours on pulse time. So basically, so this is so I jiggled the wires for the B0 for 1 centimeter deviations, which is much bigger than we expect. So we end up, if you do that, you end up with T2s down here, and sort of this is our goal. And this is after 1 iteration of that step. So this is 1,000 points in here. Most of them end up above the goal, and you can always do it twice. So if you end up below your goal, then you can always make it bigger, or you can always do it again, and presumably it will get better. Okay, so now I'm going to talk a little bit about the spin dressing field optimization. So it has to be, we have to use the frequency dependent model. And so my code includes some hacky error handling and mesh handling, because with the frequency dependent, I find it to be more challenging to get it to work with MATLAB cleanly. And so there's a little bit of that in there. And I've saved for every step on the optimizer. If it's a better value, I save it, because it does crash occasionally. Okay, and another thing we have to worry about with designing a met glass or the spin dressing coil is that the met glass heats and the wire itself heats if you're not using the right wire. And so if you're using a regular superconductor, you can think of your coil as some inductor, and then the resistor is the cladding in parallel. And so as you're increasing the frequency, the L becomes large compared to this R in the cladding, and so you end up having a significant portion of your current going down the cladding, heating up your wire, which isn't good for a cryogenic experiment. And so what we found was that because we're using such low fields, what we can do is just use a type 1 superconductor, which shouldn't heat as long as we're below our critical field. So we have to keep our low. And so the met glass heating is we decided to put, instead of building a double coil, which turns out to be very hard to get if you jiggle the wires a little bit for this sort of sensitivity. You get this, we put in a copper shield. And so this is the simulation of a RF wire, or kilohertz audio frequency wire, met glass shield, and then sort of a lead shield. And so the shielding factor on the met glass, we need about 100 or a 50. And so if we use the copper thickness of 1.7 microns, you can see that we achieve our goal at 17 microns, 34. They sell it in 34, so we can get roughly 459. And this is thin enough to not affect our squids in measurement. This is a demonstration of this material. So I was putting 12 amps through our coil. At 1 hertz, you don't see anything. And this is actually without the copper shield, so I was trying to show that it didn't work without the copper shield. At 500 hertz, you see that we start to increase. It's not past the superconducting transition yet, but it's getting close. And then that was an accidental pulse where I unplugged the power supply. But here's 1,000 hertz, which is sort of our goal. We want to be able to get up to probably around 2 kilohertz, actually. It runs away, and so we needed something to shield our met glass. And you can tell it's the met glass that's running away. So here's with the copper shield, we were able to do our field values that we wanted, roughly at the kilohertz that we need. So we can do 1.4 Gauss at 3 kilohertz, and we see a minor effect. So this is roughly saying that this probably will work as long as we have sufficient cooling power to keep the lead below around 6 Kelvin, and I think we'll be fine. The next thing I'll be talking about is the ferromagnetic cloak optimization, which is sort of fun. So in the apparatus, we have helium-3 that's being flushed into our system, because that's our detector. And so this is roughly the path of the helium-3. I think it actually goes out here somewhere more, but it's not too important. And so we get flushed down there. So the helium-3 basically travels from here to here via heat flush. I'm not going to talk about that, but it's a fun process. You should look it up. It's basically a phonon wind, goes from hot to cold, and so helium-3 gets pushed from hot to cold. So without the cloak, you can see that these field lines are messy. And we don't want that. We want to be clean. And with the cloak, you can see that they're sort of nicely routed around this superconductor, our superconducting shield. so that there's not too much disturbance. So I created an analytic model to try to account for this. Basically, what I do is I model this so that the only real non-uniform region is basically from here to here. So so if we can, if I said that if I know the rate for a tube of infinite length, then I can basically estimate the tube, the relaxation that's generated from just passing through this short section, and I can sort of take advantage of the fact that this repeating transform is the same as the real part of this transform is the same as the transform for just this section, and so we can get a similar strength for the relaxation for an infinite tube, and then we simply so this is what you get if you do that, and you see that your conditional density is altered by this convection current here, and so it basically acts like a shift in V0 that's combined with the spatial harmonic and the velocity of the current flush. And then so you can estimate your magnetization by the rate it's relaxing, the length of the thing you have to go through, and then the average convection velocity. And so I basically developed an optimization simulation code to track this, to check these results basically. And so what you can do is it can import a COMSOL model into a C++ code using just a tricubic spline. And then it solves the spins with fifth order Runge-Kutta. So it's C++, similar to Ricardo. That's a grad student at Caltech who's written some code. It's fifth order cache-carp. It integrates a scattering kernel. So this is the scattering kernel. This is how it determines whether the helium-3 is going to scatter off a phonon or not. So it's a regular scattering rate. And the rate is determined by this diffusion coefficient, and this diffusion coefficient is determined by the temperature at the point, at the position. And so it gets a new velocity. Each particle gets a new velocity based on the Maxwell-Boltzmann temperature distribution at the position, which is temperature dependent, which is position dependent, and the convection velocity, which is also position dependent. Okay, so here's a movie of that. You see it flows from the entrance to the cell, where you can see it's sort of moving around there. This is the polarization that you get from that, from a 5⁻⁻⁴. So if I use this theory I use this theory to optimize the positions of the cloak, where I optimize the number and the position of each one of these cloak strips. I get, this is my distribution. This is what it looks like in the end. This is the field along the helium-3 path. So the helium-3 comes from the top and goes down in. And then if I use the simulation for this, I end up with the polarization at the end of 99.8. This is the average position of the spin particles. This is the average field they experience. So that's good enough. So now I'm going to talk about the pulse bar apparatus. So this is a systematic study apparatus. We're going to try to learn all of our techniques that we're going to use in the SNS in a small scale that can be turned around quickly at North Carolina State and their reactor. So you guys are outside my window. So basically, so the apparatus, the cell is here. You can see there's a magnetic field here. We have UCN coming in here that enter the cell, and helium-3 comes from above. And so we can do all of our spin techniques and try to measure correlation functions in this. And it has a turnaround time of about a week instead of 6 weeks, so we can get a lot of data a lot quicker. But you can tell it's very compact. This is sort of a challenge to design these coils. Again, we use the superconducting end cap technique that eventually allowed us to get fields that we require. And we also use the superconducting as the boundary flux, and this is because the spin dressing coil would just heat this whole area up like crazy if it was using copper or met glass. And so we have to use the superconducting. And this is actually makes it even harder to build the coil than the ferromagnetic return, because the absolute wire position becomes more critical. Here's what the coils look like. yeah, you can, so I have a lot of restrictions, as people have mentioned, that I have a tube here that I can't put wires through. I have a tube here that I can't put wires through. And so this is basically what the solver finds as an adequate solution to the field, uniformity problem. I get it to T2 of about 1,000 seconds, which is above the goal, with a current, of 58, 580 milliamps. The spin dressing has a 33 turn solution. It wanted to have wires here, obviously, but we can't. And so, at any rate, yeah, it solved it. Seems to be good enough. And I think my time's up, so I guess I can finish there. I guess I can do some conclusions. There we go. Yeah, so the nEDM can benefit from spin dressing. We can relax. The relaxation can be minimized in the magnet design with the theory. The Fourier modes are a convenient way to do a volume average minimization. Heat flush is fun, and it looks like it'll work for us. Yeah. Oh, and then this last one I didn't go over. All right. Thank you.
Thank you, Chris. Does anyone have questions?
Hi, it's Beatrice. I would like to ask a quick question, if possible.
Please.
Can I go ahead?
Yes.
Okay. Chris, thank you. I had a quick question. Maybe you said it and I missed it, but you briefly said something about the shim coils for the EDM experiment. How many do you already have an idea how many you want to use? And
I'm sorry, can you
are they
repeat
going to,
my headset turned off in the middle of your question. I'm sorry.
okay,
Can
you
restate
mentioned
your question?
you mentioned shim coils for the nEDM.
Right.
And
Mhm.
how many are you planning? And like how many
I
power
think we're
supplies, how many
planning on.
coils?
I think we're planning on 10. I think we need 10 shim coils, if I recall.
10. And do you? Yes, go ahead, please.
Yeah, 10. No, 10. And so what I do usually, for the shim coils, what I end up doing is for a lot of it, what I do is I make shim coils for the linear ones, and then but then I just make them so that each pole can be tuned individually, and so you can get basically so you don't quite get a quadratic, but you get something that's even or odd symmetry of the cell, and I think that's sort of a really important thing to have control over, because the odd gradients are sort of the ones you want to avoid, because they contribute to geometric phase and relaxation much stronger than even gradients.
Yes. So you do that by superimposing the coils then, or?
No, I think we're gonna.
You want to
as
have
of right
dedicated
now,
coils for each of the modes you're most
yeah,
interested or most
right.
worried about?
Well,
okay.
right. So but there's only what? There's only 1, 2, 3, 4. So there's five of those coils, and then we'll split them into, so each pole can be tuned, so you can get even and odd. And then I think we're going to have a few extra ones just to tune away some of the even harmonics that are that will arise. And so that's the plan right now. Obviously, if we need more, we'll wind more. We have a couple surfaces where we are just planning on winding shim coils and sort of fixing them in place with epoxy, based on what we see when we first turn on the coil, I think.
Okay, yeah, that makes a lot of sense. But you're not for the shim coils, because we are always wondering if for the shim coils we think it's not probably going to be worthwhile to do self-shielded shim coils, but yeah, because the currents are much lower. Self-shielded shim coils,
right?
Because they carry much less
Yeah,
current than the main coil, right? No, okay, thank you. That gives me a good idea. Thanks for that.
Well,
answer.
we do have a flux. We have a met glass flux return for the shim coils as well, so they in a sense have a return coil.
Okay, thank you.
Great. Thank you, Chris. So our next speaker is